Welcome. Hey, I want to just remind you that we're going to put this particular set of notes on page 67 and 68. So make sure you write 3.2 at the top of that because this is from the new section in chapter 3. We're building on this idea of displacement and distance and really taking a look at position. Remember, we've talked about physics is the study of movement. It's the how and the why things move, and really putting some organized mathematical equations or mathematical models to work regarding how things move. And one of the ways that we can analyze how things move is looking at the change in their position over time. We can look at that as a distance, like an overall distance, as speed, or we can look at it as position. And we'll talk about the difference really between speed and velocity today. So we're going to look at one dimension of motion and use the equation for speed and velocity in just one dimension. And analyze those motions and be able to solve for speed and velocity. And then also be able to define and identify positive and negative velocities and know what the difference there really is. You'll see an assessment at the end of the presentation that has these 3 problems in it, and I definitely want you to use some space on your notes to give those a try as an example. And the terms we're focused on, I already said this, but the physics terms that we're focusing in on are speed and velocity today. So these are new equations. So go ahead and get this written down in your notes. These equations, I know you've seen one of them before, but they are going to go right along with the position or the displacement equations that we were working with last week. The first one there is what we call the speed equation. This is speed is distance traveled divided by the time that it takes to travel. And the one on the bottom looks very new and kind of scary, but it's actually really similar to the equation above it. So when I read this, velocity equals a change in position divided by the change in time. Change in position is almost distance. Now we've talked about displacement versus distance and the difference there. But a change in position is very closely related to the distance that something has traveled. So even though it looks new and it looks like wow, that's some crazy math, it's really not all of that. Speed versus velocity. There's your next heading. So speed and velocity are not just 2 different words for the same thing. They are different. And in everyday life, you could probably use speed and velocity and nobody would really care if you use them synonymously, but they're not synonyms. And in physics, we need to know the exact difference between these 2 terms and know how they're related, but especially understand how they're different. In the book, in your reading, you are going to have the opportunity to play with some equations. And I really want you to take the time to do that, to get in and use the interactive calculator that, it starts out on page 78. That's the start of the unit. Get in and use that calculator to solve problems, either for distance or solve for time or even solve for velocity, depending on what you're given in that particular problem, but use the calculator to try out some different problems. So let's start off by talking about speed. Speed is a value that's always going to be positive. So we're looking at something that's really not analyzing the direction that something is going. It's also part of this equation is that time is always going to be positive because you can't really go backwards in time. Therefore, speed is always going to be a positive number. And so how do we know the difference between moving forward and moving backward? We need a new variable. We need a variable called velocity. Velocity is defined as the change in position. So when I see that little symbol, the triangle X, we call that delta. That's a Greek letter delta, like lambda. We know lambda, that was a Greek letter that represents wavelength. This is a Greek letter delta that represents change in time. So you can go ahead and get that written down. That symbol is used all through the sciences, all over the place. And the change in something, or change in this case is position, but it doesn't always have to be position. It could be the change in time or the change in mass or the change in temperature. Whatever it is that you're actually measuring in your data set, that symbol means the change in that particular thing. This time we're talking about position. So, or this time we're talking about time, right? In velocity, it's how did time change and how did position change, and that's what gives us velocity, because velocity can be positive, but it can also be negative. We might end up with a negative position, and that will let us know something about velocity and how that object has moved. So you can, because you have a change in position that might be negative, you can have a change in velocity that might be positive or negative. And remember that positive and negative really has to do with direction. Moving forward is positive velocity, whereas moving backward is negative velocity. So here's a little sample problem that's going to give you a sense of how we approach this, right? What is the change in position? So we're looking at two values given here. First, the initial position, x sub I, which is 2 meters. And then this little dude takes a walk over to the final position, x sub f, which equals 8 meters. The equation for solving for the difference, this variable in position, is change of x equals x sub f minus x sub y. So we say final position minus the initial position. So you can plug those values in. 8 meters minus 2 meters equals 6 meters. So the change in position is 6 meters. And then in this particular problem, they're so kind, they don't make us calculate the value of time and the change in time, so they just give it to us as 2 seconds. But when we plug all of this in, you can see that this becomes 2 values here. And what I want to point out is that what we're dealing with is that the change in x equals the final position minus the initial position. So we can just like substitute out this whole expression for the delta x. So now you can see what we have is this value here is our x sub f, or our final position, and this one minus is the initial position, or x sub I. And so those have been plugged in here and basically just switched out, right? One for the other in that equation. You could switch, either expression can stand in for the other expression since they are set to equal. And so when you solve that, first remember PEMDAS, you got to take care of what's in the top here and do the subtraction, and then divide. And so we got this, like we got to take care of this guy first. Whoops, sorry, terrible parentheses. So 6 meters divided by 2 seconds. And in your units, you now have what's called a derived unit. You have meters per second. So 3 meters per second is the answer for that one. Whoops. All right. But that is in a positive direction. On the other side of that, what if the person were to start at 8 meters? So now our initial position is different. Before we had the initial position at 2. This time we're going to do initial position is 8 meters, and that individual decides to walk in the negative direction. Remember, the negative has to do with direction. And they end up in their final position at 2 meters. So it's going to look a little bit different. Same 2 seconds. It's going to look a little bit different because I'm basically going to switch these values out. The man is now headed in the negative direction. So it's his initial position, his final position is 2 meters, and his initial position is 8 meters. And so you can see these are switched, but it's still the same equation. But when we do this, 2 meters minus 8 meters, that is a negative 6 meters, divided by 2, and you get negative 3 meters per second. That tells us where he's going, which direction. That is because it is a vector. Velocity can have negative or positive values, and the sign of velocity is going to tell you the direction of the motion. Velocity is a vector. A vector is a type of variable which includes directional information in a mathematically useful way. And just for fun, I have this here for you, just in case you remember this guy.
Hey. I'm applying for a new villain loan. Go by the name of Vector.
Wait for it.
It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, as I'm committing crimes with both direction and magnitude. Oh, yeah!
So you can rewind and watch that and get that definition down for yourself, but it is, you can see that it's a variable that includes directional information, the quantity that includes both direction and magnitude. Positive and negative velocities are much like positive and negative positions. There can be a positive position and even a negative velocity. Here, I need a volunteer to show me how. I don't know about that. I think we'll go with this guy. Positive position, negative velocity would be him going in the negative direction. Velocity, remember, is a change in position, so there has to be some kind of movement taking place. Can there be a positive position and a negative velocity? The answer is yes. Can there be a negative position and positive velocity? So we got this little volunteer, as they say. Negative position, and then a change in position in the positive direction will give negative position and positive velocity. So it is definitely possible. It all depends on the origin. So what is the initial position? Remember that from our displacement analysis. Positive and negative positions and velocities. Let's see what we got here. Can there be a negative position? I think, negative position, negative velocity. The answer is yes to that one. And then the last one, can it be positive position and positive velocity? So positive position, positive velocity. If the origin is positive and the velocity is positive, that is possible. We can have both positive position and positive velocity. All right, so some terms that you need to get down into your notes and to kind of illustrate as you go, that these are really helpful diagrams for that. So you don't necessarily need to draw like 3 different balls. What this is trying to emulate is that something started out in an initial position and now has shifted position. So that's this guy right here, right? And then the arrow, though, that is important. This is just speed. It doesn't matter which direction necessarily, but you have a change in position, right? Distance. We used this kind of setup like in wavelength, but this is how we would represent distance in a drawing, the distance between 2 objects. Whereas velocity, you can see that there is a symbol attached to the speed now. And here we have negative, and it has to do with the direction that it's going. So tell a story that illustrates how each picture relates to the meaning of each word. Position, displacement, origin. Draw them up, right? These are coordinates, remember that? Our X and our Y. And now coordinates are used for dealing with motion in 2 directions. So you don't just have like a horizontal line. Now you have motion at an angle. A vector is symbolized by an arrow. And obviously the head of the arrow, the triangle at the end, is going to tell us about the direction that it's going. Okay, so we are to the assessment. I gotta get off the focus. Sorry about that. I'm like, hang on. There it is. All right, so go ahead and pause. Get this down on your notes. Pause and give it a chance give it a solve. Okay, so you're back, right? So for that particular problem, the speed was 16 meters per second because the velocity could be either in the positive or the negative direction. It didn't tell us where that swallow started. It didn't tell what direction it was going. And so we don't actually know its velocity. We know that the velocity could be either positive or negative, and so we have to give two answers for velocity, whereas speed is defined as just the values. And so you would take the distance divided by the time. So 80 divided by 5, which is 16, but that would be meters per second. And then write an English sentence that means the same as this equation. Go ahead and pause and try to write that out. And then velocity is the change in position. And you can say is, or you can say velocity is equal to the change in position divided by the change in time. This example right here is the example of positive position and negative velocity. So where someone starts on the positive side of the origin, but is moving in the negative direction. And then, as I was saying, I would really like you to dive into some of these problems. And so you can see there's a lot more problems to solve. And I think, let's take a look at the book. Well, I don't even know if I can switch to the book, but I've got the book open. Let me just click on speed calculator. So there's like 6 different problems, A through F. So if you see these little buttons down here, oh look, I can get that focus again. So A, B, C, D, E, F. There are problems attached to each of those. So if you go into the speed calculator and you click on one of those, you'll see a problem come up, and you can take some time to solve it and get some practice in that way. So this problem was 30 meters is the travel distance, and the time is 2 seconds. What is the car's speed? Doesn't ask about direction, so it's just asking about speed. If you go a distance of 45 meters at a speed of 16 meters per second, how long does it take? How long does this trip last? So now we're trying to solve for time. So one of the things that we dealt with the speed equation was we need to rearrange a variable for what we are solving for. So you can see that this is set up with 16 meters per second equals 45 meters over s. I'm going to go ahead and write it out like this because I think it's really valuable for you guys to see what you could put on paper. Whoops. Actually, just for fun, let's change the color of this. Always looks like I'm like teacher writing, right? In red. So 16 meters per second, we know, we can plug that in. We know 45 meters is the distance. Whoa. There we go. But we don't know the time. And so we need to solve for time. And in order to solve for time, we can do some quick algebra here. If we multiply this side by time and multiply this side by time, then divide by and let's go ahead and divide by 16 meters per second. I'm hoping you're catching what I'm doing here. I'll tell you, this is the opposite. So I'm just doing a little algebra and showing you what the steps for rearranging that equation are by using algebraic manipulations. So these two will cancel out. These two will cancel out. And what I'm left with is t equals 45 meters. Whoop, whoop. And because I can just multiply across, right, and multiply across, then this becomes this fraction of 45 meters divided by 16 meters per second. And guess what? When I do the math here, the meters are going to cancel out. The second is divided by, which convert like in a confusing manner, just so you know, it's going to be per second. But 45 divided by 16, we use our little calculator. Oops. Oh boy. Sorry about that. And hopefully you can go back and rewind it. I didn't actually mean to, erase it, but 45 meters divided by 16 meters per second gives us 2.8 seconds. Or you can, rearrange the equation before, but you can always plug in and solve for the one that you don't know. A fox runs at a speed of 9.7 meters per second for 12 seconds. How far does the fox run? Let me see if I can. Let's use purple this time. Okay, so things that we know. We know the speed, so you can plug that in. And we know the time. And then it asks us, like in the book, asks you what you're solving for. And so you can plug that in. In this case, we can do it by hand as well. 9.7 meters per second is equal to the distance over 12 seconds. Easy, easy, cheesy peasy here. Going to do the opposite and multiply by 12 seconds. But if I multiply one side by 12 seconds in order to keep it equal, I have to do it to both sides. These cancel out, leaving me the distance. So 12 seconds times 9.7 meters per second, and I cancel out the seconds. It's going to leave me with meters. Just like that. 9.7 meters per second times 12 seconds is 116 meters. And that's how we would solve for the speed. Now, velocity, whoopsie, is a little bit different because you have a change in position. So you're looking at finding the change in position and the change in time first. This is like your step one. And then you can plug it into the velocity equation and do your step two. So you enter your initial values for finding the change of each of those. And then, so we've got a car stops at 30 meters and finishes at 10 meters. So where does it starts, that's initial, and its final is 10, and it takes 2 seconds. So the final time is 2, and we assume, since we weren't told anything else, that the initial time would be 0. What is the car's velocity? Negative 10 meters per second, because we end up with negative 20 meters as the change in position. You can see that this car must be moving in the negative direction. A car travels at 15 meters per second. 4 seconds after starting out, it is at a position of 40 meters. That is a strange way of saying that only 4 seconds have transpired. And we still have our initial time at 0, but you're going to have to pay attention because they may add in where your starting time is not actually at 0. So what is the car's change in position? Where did the car start from are the questions that were being asked, which is different from just what the velocity is. So you can see here we had to plug in the final and the initial so that it starts initially let me go back. So we put in the change in time because that's what we're given. And we had the velocity. So a car travels at 15 meters per second, and that's what we plug in. I almost messed myself up. After starting out, and is at the position of 40 meters. So we knew our final, we're given our final right here. So this little guy is x sub f. And we have our velocity. If we know that we can kind of work backwards. We use our time Oh, here's where it says 4 seconds. This is our change in time. And so we can plug that in here. So now we work a little bit funny because we work backwards. This is our step 1. And we have to find the change in position. Hang on. We have to find the change in position. And once we find the change in position, then we're able to take this value here and take it into our change in position and find, so we have our total change in position, 60 meters, and we know our x sub f, so then we're able to calculate that negative 20 meters. And then we know that the car started from negative 20 meters. On here, like it's set in time, or it's set like it's a picture of what you're doing. It's hard to see that this is like step 1, and then you have step 2. At first you wouldn't know this. You actually are solving for that. And so when you set it up, that's what would be missing. Okay, now I can clear it. There you go. All right. So see if you can come up with an example where each object might actually move at this particular speed. 1/10 of a meter per second, 1 meter per second, 10 meters per second, and 100 meters per second, and then 1,000 meters per second. I'll give you the answers, but you pause and write those down, and then I'll go ahead and give these to you here. So the tip of the second hand of the clock is about 1/10 of a meter per second. You walk about 1 meter per second. 22 miles per hour, or a brisk bike ride, is about 10 meters per second. Just at 100 meters per second, it goes way faster than we would go in our cars normally. But so a supercar's top driving speed, which would be, topping out at 220, and then 2,200 miles per hour is the equivalency of 1,000 meters per second, which is about an F14 top speed. And I think we're at the end of things. So I'm trying to make sure that my mouse is clicking properly. So you can go ahead and kind of go back and do what we call reps on your notes, kind of go through and add on, pause, whatever you need to do to make your notes a really great study tool. I'm going to just go back really quick and take a look at slide 2, which were our objectives. So were we able to describe one-dimensional motion using the equation for speed and the equation for velocity? Were we able to analyze that motion, determining whether it was speed or velocity? Do we have negative position or negative velocity? And then just be able to define and identify what positive and negative velocity looks like and how it can actually be produced. So I hope that you get a chance to practice. I want you to practice on those equations, and we'll definitely give you some time to practice at the beginning of next week. So that wraps up the first semester in terms of notes. And now we're just going to put some things into practice.